Can you switch on your video? Hi Manish. Hi. Hi. So any doubts till now? Manish, hello. And Vishwa Prakash, any doubts? हाँ
सिंगुलर सॉल्यूशन एक बार एक्सप्लेन कर देना।
ठीक है वो मैं समझ गया वो प्रॉब्लम क्या है। मैं ओके आई विल डिस्कस इट आफ्टर द एग्जाम। ओके it will not be there in the exam, singular solution for sure. I will explain this because while explaining this I will tell you something more on this singular. I will come to that topic again in the second order case. Okay, there I will discuss more on a singular solution. Okay Manish, okay good. Manish, okay, good. Yes, who Manish Chauhan, Sanjeev, Atharv, Ankit, Anu, Nirmal, Kritika, Shammi, any doubts? So just a minute. So I have already added all of you in 3 groups, 20 accordingly something like first group it's like 20, 22, 21, 18 like that, so that all the 60 students are there. So the thing is that you will be joining only with that group for the exam on Monday. Okay, is it clear to all of you? In the MS team I have created 3 separate groups. Of course the one person can see only his group only, his or her group, like it will be named like that: A, B, C, MTL 603A exam, 603B exam, 603C exam. All of you got it? Yes or no?
Yes sir.
Yes, okay. So this is the first point. So the exam will be of 45 minutes. Yes, thank you Shammi. Exam will be of 45 or 50 minutes, let's say. Okay, so and I will give you 10 minutes for uploading, 10 or 15 minutes for uploading in the grade scope. Is that clear? Not more than that. 15 minutes I will give. Of course, if you have some problem with the grade scope, then I will of course you can send me in through my email or something. But please be sure that all your internet connections, everything is fine. Otherwise, another point, unless you switch on your video on that day, I will not going to take the exam. Okay, is that clear to all of you? Is that clear to all of you?
Yes sir.
Yes,
yeah,
sir.
On the exam day you have to be, this is a proctored exam, so on the exam day you all of you have to switch on your video. Okay, so please make sure your connectivity and the data usage and everything. Okay, please make sure. I will send an instruction today, and the exam will be up to lecture 7, I have already said. And anything else you want to ask me regarding the exam? So you will join with your respective group. Okay, don't join in this MTL 603 course page. Is that clear? Don't join in this in this page. So you will get an invitation. Of course, there is a link to join. You will get a link tomorrow or Monday. You will receive the link. With that link only you will join. Is that clear? Huh?
Yes.
All of you, Manish, Kritika, Sanjeev, Shammi, all are clear?
Yes sir.
Yes, sir. Yes, sir.
कितने मार्क्स का होगा?
हाँ क्या हो रहा है? मनीष बोलो.
कितने मार्क्स का होगा?
वो 20 या 15 कुछ देखेंगे. I have not yet prepared the exam paper. So okay. So anything it will be all two quiz will be two. There will be 2 quizzes, right? Quiz 1 and quiz 2. The weightage is 30%. The weightage is 30%. Okay. Okay. So anything else you want to ask me? You want to clarify for the exam? Please tell your friends also. Please join with that link only. The link which will be sent tomorrow or day after tomorrow. Okay. Clear? The exam lecture 1 to lecture 7 is the syllabus. You have to switch on your video all throughout the exam, and you will be given at around 50 minutes the exam and 10 or 15 minutes for uploading in the grade scope. And you know how to upload in the grade scope, like according to the question number 1, 2, 3, like that. You know, right? All of you know, right?
Yes.
Okay,
Yes.
you know how to do that. Yeah. So that is all. Anything else you want to ask me? Please tell me. Please.
Sir, is there anything else that is excluded from the syllabus? Like you said, singular solutions will not be there.
Singular solution, I won't ask. This is just I just said this because he was asking me, because singularization we will do in the next chapter, in next to next chapter, in a more detailed way. If something called something else. So no, nothing else. Nothing else. It is mainly on the characteristics, and of course the nonlinear things are also there.
Okay.
Okay. Yes, Atharva, clear?
Yes, sir. Yes.
Okay, good. Let's start. I will do 3 examples today. Not much. I will do 3 examples of these weak solutions. Okay, 3 examples, and see how we can use this Rankine-Hoogenite condition to resolve this problem. Okay, let's start. Okay, let us recall. Okay, you are not able to see. I think I have to present it now. Are you able to see the whiteboard?
Yes, sir.
Okay. Okay. So recall. Can anyone tell me? Recall what is the weak solution? Of course, I will also tell you something on the integration by parts. Solutions. What is that? For the equation ut plus f of u x equal to 0, let's say t positive and x belongs to R, and u of x naught 0 is hx. So what is the definition? Can anyone tell me? Oh, so where? Just a minute. Where f is a continuous function. Okay. So what is the definition? Can anyone tell me? What happened?
So it is a bounded measurable function.
Yes. U is said to be a weak solution. U is said to be a weak solution if U is a bounded measurable function such that there holds U Vt plus f of u v of x dx dt minus infinity to infinity u at x0 v at x0. This equality should holds for every v in cc infinity of r cross. That clear? So we call this is a weak solution. U is said to be a weak solution of the PDE. Let's say star. The weak solution of the star if U is a bounded measurable function such that there holds this relation. This equality should holds for all v in cc infinity. And my question is why we need this notion of weak solution? Can anyone tell me why? Yes.
I have a doubt about this definition. I mean, in the definition, we take U to be bounded. I mean that we can actually, if we take general function, for example, U x to be x u x y equal to x plus y, then it is not bounded. But we can create a PD where the solution is not bounded. So will that solution be?
Yeah. Just a minute. We require this boundedness of measurable function because can you guess why we need? Just to make sure that this
the
defined.
integral exists.
Integral, if we just remove the, we don't actually need this condition. Okay, we can remove this condition provided we can assume the integration this integral exists. Is that clear?
Yes, sir. Yes.
Okay, thank you. So that if this integral makes sense, that is the reason. And actually another point, you see, you need bounded to be in on a compact set, because Vt, the support of V is a compact set. So outside a compact set, Vt, if you take V is a C infinity function, then Vt also is also a, if you take the derivative, is also a compact supported function. Okay, yes or no?
Yes, sir.
Derivative is also a compact supported function. So these integration actually are doing in only a compact set, on the compact set. So we need V, at least you should be bounded on that compact set so that this integration makes sense. Or in other words, as you said, this boundedness, we can drop this concept. This boundedness measurable function is not needed. Just we assume that this integral makes sense. Is that clear?
Yes, sir.
Yes, thank you. Very good point. Thank you. Thank you. Very good. So this is a definition of weak solution. So now my next question is, why we need this, why this notion of weak solution needed? Huh? Why we need this introduced? You tell me.
Because we need to define the solution at the points where the characteristic lines intersect.
Exactly. When the characteristic line intersects, we have seen in intersects where the characteristic line intersects, we have seen that at those intersection point, you have a problem in defining a classical solution. Yes. Why with the idea or the motivation is if the characteristic line intersects, if the characteristic line intersects, then the solution may not be classical. We have seen example, right? May not be classical solution. You know what is the classical solution? That means it's not a smooth solution, right? So that means then what to do with those PD, and you will see in the nature, in the physical world, all this PD when this is form of some kind of you will see some kind of Burger's equations like wave equations or something. You will see in the natural phenomena, mostly the PDEs we see, which comes from the nature, you will see that these PDEs are quite complicated, and you will see that they are mostly of this nature. That when the characteristic, that Burger's equations. Remember, I said some Burger's equations. So quasi-linear in nature mostly. Okay. So mostly this type of Burger's equation and or iconal equation, all these are non-linear PDEs, and this type of phenomena is very much obvious in those PDE. Then what to do? Then we have to study those PDE, right, in a more detailed way, and for that we need to define. We need the notion of weak solution. Okay. Also in research, when we do, if you want to do research on PD, you will see there are something called very weak solutions. There are something called mild solutions. There are thousands of way you can define a solutions. Okay. So mostly you will see that classical solution is very rare, unfortunately, because all the PD are coming from this physical phenomena, and these are non-linear in nature, and they are very complicated, and you will see the mostly the dynamics and all those things are very much complicated, and you will see that mostly these PDEs are, you have to define something different notions of solutions. Okay, so we need to define a new notion of solutions. Okay, there are many. You will see if anyone wants to work in PDE after your MSc, you will see there are many types of solutions. Okay, so like very weak solutions, something called very weak solutions. They are very much depending on the PD. Something called mild solution. Okay, so like the strong solution, something called strong solution. So something, another most general way is something, another very general way is some called that is called viscosity solution. So these all are viscosity solution. Many more. So all these notions arises. So sometimes you will see that this weak solution is also not capturing the solution. Then what to do? Some PDE are there which you cannot able to write the weak solutions also, because you have to define this equality. You will see that this is not satisfied. This integral may not define. Okay. Then what to do? Okay. So then you have to something called very weak solution. So you have to define some new notion of course. And why we are defining these notions? There should be some physical relevance, right? Otherwise, one can say I'll define this way. I define this way. You said there should be some coherent way to define all those solutions, right? So there is this is called something called physically relevant solution. Physically relevant solution. Something called physical relevant. This has to be very important. Any solution one should have some physical relevance. Then only we should define those notions of solutions. Okay. So this is side remark. I just got it. I give you this all of the side remarks. So this is just a one. This is called and of course this is a very famous one. They're mostly we use these weak solutions. Okay. Okay. Now you understand what is the weak solution and what is all those things. Now what we have done, there is something called we have studied some theorem. What is that theorem? If anyone can recall, if u of xt is a weak solution, the PDE is the same. Okay. This is the PDE we are studying. If u of xt is a weak solution to star such that, this is very important, such that uxt is discontinuous across the curve x equal to xt. But this is your curve, but u is smooth on either side of the curve. Of course, I assume that this curve partition that domain in two part. Okay, in two part. This I have assumed. Is it smooth on either side of curve, d minus and d plus. Then uxt must satisfy the condition. What is that condition? The tangential at the point, tangential vector, the tangent at the point to the curve should be equal to f of u minus of f u plus by u minus u plus. Okay. And what is u minus and u plus? Where u minus is the limit x tending to xt and x less than xt of uxt. You understand what is the meaning? And u plus is nothing but limit x tends to xt, x greater than xt. That means if I draw pictorially, what is that? This is your domain x, this is your domain t, you have a curve. This is your xt, x equal to xt. Okay. So here this is d minus, this is t plus. Okay. And what is u minus? So there is so u is smooth here. U is smooth here. This part. Okay. U is smooth. Again, this part u is smooth. That means it's a piecewise smooth function. The problem is along this curve. It has a discontinuity here. Discontinuity. Okay. We assume it has a discontinuity. And what is u minus? U minus means you know what is that? Limit from here you take the limit xt, where xt tending to x tending to xt. It tending to this curve. Okay. When you tending to this curve from a left hand side, this is u minus, and if you come to this side, this is u plus. Okay. And across the, of course, u minus is not equal to u plus. Okay. So this is a necessary condition that if u is a weak solution, this is important, not every solution. If u is a weak solution and it's smooth on the either side of the curve, then any arbitrary curve will not work. Then the curve which we will drawn in this way should satisfy this property. The proof is basically using integration by parts. The idea of the proof is the integration by parts. So first you have to take this domain. This is the boundary. So this domain first, okay, and of course it goes up to infinity, and another is this domain. So there are two boundary parts. This one boundary for this domain, and this is the boundary. And for this domain, this is the boundary. This is the boundary. Clear? Is that clear? Okay. The main idea is the integration by parts and using just a definition of weak solutions. Okay. So we arrive at the, of course, I will say in the end of this class what is the integration by parts of again. Okay. Then we remark this is called Rankine-Huganoid condition. We call this is a RH condition, or it's called Rankine-Huganoid condition. This is called Rankine-Huganoid condition. We write in this manner. If you remember, in the notational way, we write it in this way, right? In notation, we write in this way. U box is U minus U plus. F U is F of U minus F U plus, and sigma is, we say, exponent. So RH condition is, what is that? F of U is equal to sigma times box. Okay, so this is the RH condition. Okay, now let's do an example. How we will see this RH condition play a very important role in constructing a weak solutions. Okay, we will see. So okay, let me ask you something. So do you have any questions from here? Do you have any question from here? Do you have any question from here? Yes, anyone? Ankit, Anu, Anshu, Athar, Vishwa, Deepak, Dev Ranjan.
No, sir.
Do you have Shami? No. Okay.
So here we are assuming like we have only one curve.
Yes.
Like
go ahead.
Where like my function is like not smooth. These curves like could be finite also, right?
Finite means I did not understand what you mean by
like
finite.
Here I'm considering only one curve xt where my function u is not smooth.
Yes, so you are asking there may be finitely many part, right?
Yes, sir.
So like another curve, like here also, right? You are asking me, right? Yes, it is possible. Then you have to use RH condition here to here. You understand? So yes, it is possible. Okay, it might be very, very complicated. Okay, this is just a simple scenario. Okay, yes, very good.
And these don't intersect also, like
it might happen that these goats intersect. All might possibility can happen. Okay, and this I can tell you these all are the very physical relevant type. Means in physics this type of situation arises in physical context. So might happen that this curve intersect along here it is discontinuous, here discontinuous. So all type of possibility might happen. Okay, yes. Just a simple, it's a toy situation, you can say. It's a toy theorem. Just a simple that there is a one curve where it has just along this interface we have a discontinuity. Okay.
Okay, sir.
Thank you. Let us do an example. Uy plus ux equal to 0. X belongs to R. Your favorite example. U of x0 is equal to h of x 1 when x less than 0, 1 minus x. We have done this example in a detailed manner. 0 when x is greater than. So can you tell me what is the solution? You take the space curve s comma 0 comma h of s such that s belongs to R. So what is dx by dt? Huh? What is dx by dt?
Z.
Yes. dy by dt 1 dz by dt equal to 0 with the initial condition x of s0 is s, if y of s0 is 0, z of s0 is h of s. You know the solution is y of st is t, z of s is h of s, and x of st is s plus t h s. You can solve this and immediately get this. Okay? Okay. So just look. So if you remember well, then we have done this, that the characteristic curves are characteristic curves are you remember x is equal to y of t of hs plus s, but we know that t is just changing the variable y. We know this x equal to y of h of s plus s. So we have drawn this, if you remember, we have drawn these characteristic curves. Okay, so just see, this is y plus s because hs is nothing but 1 when s is less than 0. Sorry. Yeah, so it is 1. So y plus s when s is less than 0. It is s when s is positive, and this is between something like s between 0 to 1. So it is like what is called y into hs is 1 minus s plus s. Okay. Okay? Is that okay? This is the characteristic curves. So you tell me how we will draw this curve. So if you see that, so there are two parts. If you remember, this is 1, this is 0. So s less than 0. Here is s between 0 to 1, and this is s greater than 1. So at s equal to 0, the characteristic y plus s. That means we know that dx by dy, the speed is h of s. Okay. So this is 1. H of s is 1. Okay. So this is okay. Oh, I should not draw like this. Anyway, okay. So I should write 1 here so that okay. Now y s equal to s greater than equal to 1, we have x equal to s. That means like this. And between 0 to 1, we have 1 minus s. This is s, and this is 1 minus s, 0. So this is like this. So the problem is, so you can write down the solution. The solution is what is the solution? The solution is for y less than equal to 1, because after that there is a hit. This is y equal to 1. So for y less than equal to 1, we have a smooth solution. U of strictly less than 1. This is 1 because you know that. What is the solution? The solution is z. What is the solution? Is z. You know. So z equal to h of s. So that is u of xy is equal to 1 when x is less than y. when x is less than y. This part, okay? And then it is 1 minus x by 1 minus y when y is less than equal to x less than 1. And it is 0 when x is strictly positive. Yes or no? We have done this in a very detailed manner. You remember, all of you? Yes or no?
Yes.
Yes, sir. Yes, sir.
Okay,
Yes,
good.
sir.
Very good, very good. So this, but you have to be careful that this is defined only for y less than 1. But whenever y is equal to 1 or greater than 1, there is a intersection. Before that, see, before that there is no intersection. There is no intersection. Y less than 1. So we can define for y less than 1, we can define it very nicely, right? Very nicely we can define. This is the solution. Now let's see what happened at y equal to 1. If we want to define, then of at ux x1, or you can say y, this one is 1, this is equal to 1 if x is less than 1, and this is 0 if x is greater than equal to 1. So there is a discontinuity. So this is a discontinuity. Discontinuity at y equal to 1. So sorry, there is no hope. There is no hope we can define classical solution. Okay, so that means we have to define something, a weak solution for y greater. So our aim is to now define, y greater than equal to 1 notion of solution. Definitely we can't do for with a classical solution. Okay, that means we have to tone down our notion of solution. That means we have to define. So answer is we need to define weak solutions. Okay, but you should remember weak solution, there is a intersection of the characteristic. That means along that curve there is a, along this curve, if you go through, so this curve, see, if you go to this, along this curve there is a discontinuity, because everywhere this will be intersecting. Every point is a, so for y greater than 1 there is a problem. How to do this now? How to define weak solution? Define weak solution. How? Define weak solution for y greater than 1. Clear? Is that clear?
Yes,
you understand what happened? So situation. So first of all, if you want to define a weak solution, we should see that curve. So just a minute. Note that the initial data, that means u at x comma 0 equal to h of x. The initial data for x less than 0, we want u equal to 1. Is that clear? Is that clear? Because why? Go to the. So what is h initial ux? H is 1 when x is less than 0. When ux 0 is 1 when x is less than 0. That is I have written. Note that the initial data for x less than 0, we want u to be 1. Clear? Is that clear? While the initial data for x greater than 1, what we want? For x greater than 1, what the initial data requires? Huh?
0.
And while the initial data for x greater than 1, we want u to be 0. That should also hold for, if you write down, we want to define the solution from here onwards, right? Here everything is done, right? Yes or no? Y less than 1, everything is done. Yes or no?
Yes.
Yes, sir.
So for here we want u to be 1. So above y equal. So let me draw. Always draw the picture, then it will be clear. This is y equal to 1. So we want here u to be 0 because it is x less than 0. So this is your x greater than 1. So along this plus place we want u to be 1. Yes or no? Yes? Yes or no?
Yes.
Yes. Here we want u greater than 1, at least the initial data, and u greater than 0. Okay. Now let us because we want to find that xt, that x equal to xt, that interface curve. Okay.
Sir,
Now
for
let us
x,
try.
Sir, for x greater than 1, we want u to be 0.
Sorry. And here is 1, right? Yes.
Yes.
Thank you. Now let us try to make, with this idea, with this concept, let us try to make a compromise. Make compromise by defining a curve x equal to, this is a y plane, so I have t or y, I have used y, right? X of xy such that u is equal to 1 to the left of the curve, and u equal to 0 to the right of the curve. You understand what I want to say? So just get this idea. So what I want, we want to find a curve here. This is your x equal to xy. So that here it is u equal to, let's say here it is u equal to 1, this part. So I want to make a curve such that u equal to 1 here and u equal to 0 here. Okay? Is that clear? Is that clear? I want to find a curve such that in the left hand side it is u equal to 1 and the right hand side u equal to 0. Just to get an idea. Just from this I got an idea. Is that clear? So here
Yes.
it is 1, here u equal to 0. So you have to find some curve. So I decide I will put here u equal to 1, 0, full here u equal to 0 and full here u equal to 1. Clear idea? Okay. That is your u minus will be 1 because here I want u equal to 1. It's a constant. So when they take the limit from here, it will be 1 and u plus will be 0 because if you take the limit from here. So for y greater than 1, for y greater than 1. From here I want to draw the curve. Okay. That's clear. Okay. So this is just to get it. So what is RH condition now? Rankine-Huganoit condition will tell us that what is FU? Okay. So for this problem, what is FU? Can you tell me? What is FU for this problem? This is your just tally with your equation. F of u x equal to 0. So what is FU for this?
U.
U square by 2.
Exactly, u square by 2. Good. U square by 2. Because if you see f of ux is 2u ux. Of course, if u is smooth. So I have assumed in the left hand side u is smooth, in the right hand side u is smooth. Okay. So fu is this. Okay, is that clear? Okay. So what is f of u? Rankine-Huganoit say equal to some sigma. So what is that? U minus square by 2 minus u plus square by 2 is equal to sigma times u minus is. So if you put what you will get, sigma. What you will get? U minus is half, u plus is 0. That sigma is your x prime of y. U minus is, what is u minus? 1. So this implies you got x prime of y is half. Is that clear? RH condition says that if I assume u minus and u plus and there is a interface, there is a problem. If I do this, then what is x prime y? Half. Is that clear? Huh?
Yes, sir.
All of you?
Yes.
Okay, good. That means I got x prime of y equal to half. Another thing, this curve x y xy comma y passes through the point 1 1. Agreed or not? Because the problem is we have to start from here where y is greater than equal to 1, and of course this is the heating portion. This is also x equal to 1. Yes, so I want to draw a curve from here. Is that clear? Passes through 1 1. Yes or no? Yes or no? Because if you just see here the point, so from here from this point the problem starts. So from here I have to define some new curve, so that here it is u equal to 1, here u equal to 0. So it passes through 1 1. If you write down the equation which satisfy and passes through 1 1, you will see that x minus 1 is equal to half times y minus 1. You will get it. Okay, and this imply x equal to y plus 1 by 2. This is the equation of a what is this?
Straight line.
Straight line. Straight line. Can you now draw the picture? It's a very interesting picture. You will see. So the problem is here. This is 1 1 point. Okay. Okay. So this is the equation. Let's say this is x equal to y plus 1 by 2. It passes through 1. Okay. And this is the line x equal to 1. X equal to 1. Here you define all here. This portion. You define u equal to 1. Clear? All this portion you define u equal to 0. And inside, so you have done here, you have done here. So only place left here. You define here u equal to 1 minus x by 1 minus y. Clear? So the solution is, therefore, I will draw again. Therefore, y greater than equal to 1. The solution u of xy is 1 if x is less. This we got, right? This we got here. The RH condition says that the left hand portion u equal to 1 and u equal to 0. This we got, right? So this is 1 and 0 if x is greater than equal to 1. Clear? Now you have to define the complete solution. So y less than 1, you got u of xy equal to 1. When x is less than y, you know that 1 minus x by 1 minus 1 when y is less than x less than 1, right? And 0 when x is greater than equal to 1. And for y greater than equal to 1, you just define this function. U of xy is 1 if x is less than y plus 1 by 2, and if for y greater than 1, the uxy, and 0 if x is greater than y plus 1 by 2. So if I again draw the picture, what is happening? So this is the line here, x equal to y. Y is less than x. That means here y is less than x less than 1. That means this is your x, this is y. So this portion, this portion is this y is less than x greater than less than 1, right? Inside this portion, this portion, you define u to be 1 minus x by 1 minus 1. Yeah, clear? So in this region, you define u to be this, and this is the straight line x equal to y. So this is the straight line x equal to y plus 1 by 2. Okay? Here you define whole portion, this portion, whole place. Here you define u to be 0. Okay? And rest of the portion, in this portion, you define u to be 1. Is that clear? And this is your discontinuity line, RH. You understand? So in these portions, y is this. Here it is 0. Here this is 1. Is that clear? See how beautifully with the help of each condition we define. Is that clear? All of you? Huh? Yes or no?
Yes, sir, it's clear.
You do it in your hand, you will understand. Once only you do, you can understand. Okay. So this is a very beautiful way you can define with using the RH conditions. Okay. Now one more example I should do. What is that example? So what example next? Next, what should we do? Which example? Remember? ut plus ux equal to 0. X are positive and u of x 0 is equal to h of x. You remember, right? 1 if x is less than 0, 0 if this is very easy. So the character, you remember the characteristic curves are x equal to t hs plus s. Remember t plus s if s negative, s if s positive. So you have this situation. It intersects for every s positive, the characteristic curves intersects. You remember this situation. This curve intersects. Can you tell me how to do now this how to resolve this? Very easy. This should be very easy. So you just think here what is u? What is u here? Huh? For x less than 0, what is the initial condition? And for x greater than 0, u is this side, u is 1 and 0. So you want to find some curve from here which passes through 0, 0. On the left hand side, if you wish u to be 1, and on the right hand side you wish u to be 0. Yes or no? So what should you should do? So you want to this. So the idea should be you want to define a curve from here, so that in this portion u is 1, and here in this portion u is 0, and find this. Yes or no?
Yes.
So u minus is 1, u plus is 0. Okay, and of course again of your fu is u square by 2. That portion is there. So if you write down the RH condition, this is very simple. RH condition. What will be the RH condition? X prime of t is half, again half. If you write down this half, and again this curve passes through 0, 0. Passes through 0, 0. This means xt equal to half t. This is the equation of a straight line. So how to define the weak solution? You just take this. This is your line, x equal to half t. In this portion you take u to be 1, and on this portion you take 2. That's it. So the solution uxt is 1 if x is less than t by 2. It's 0 if x is greater than equal to. Okay? Is that okay? Very simple. So here all this portion, if you take u to be 1, and along all this portion you take u to be 0. That's it. Done. Okay?
Sir,
and of course if you check this is a weak solution. Of course you have to check this is a weak solution. You can check easily, and this is your curve. Yeah, tell me. Yes.
Sir, for s less than 0, there was no intersection. We could have defined classical solution there. But we defined the weak solution for whole of the domain. Why did we do that?
Yeah, because you will not be able to define classical solution for X positive, right? For X positive, you will not be able to define classical solution. Agreed?
Yes.
That is the, and here you can define U to be 1. The classical solution U to be is 1 actually. So the problem is here you cannot define the classical solution because the characteristic intersects. Now what you are saying that now you in the whole domain you are getting a weak solutions, right? That is your question, right?
Yes.
Yeah. This is something a compensation. So you want to define the solution for a whole domain. The solution of a PDE means when the PDE is prescribed in a domain, that means you have to find a solution in the whole domain on the domain where the PDE is prescribed, right? So it will not give this if you just solve for half of the domain, then this is not a complete solution. Is that clear? So you want to study this PDE in a whole domain. And in the whole domain, there is no possibility that we can define a weak classical solution. So we have to tone down. And for that, we needed to define a weak solution. And for defining a weak solution, the necessary condition is that we need to find a curve which is satisfy the RH condition. So that only we can define a type of weak solutions, right? That is the reason we do this. Is that clear? Of course, in that way, we are losing that this is a classical solution in some domain. Of course, this is a classical solution. We are not sorry. We are not losing anything. If you just see is this domain, this is a classical solution. This is in this domain is a classical solution. But in the whole domain, this is not a classical solution. This is a weak solution because of discontinuity. Is that clear now?
Yes, sir.
Okay. Now one more example.
Also,
yes.
So we can also like take U to be 1 at X equal to T by 2 instead of taking it to be 0.
I cannot hear you. Yes, tell me.
Hello. So
yes.
like we defined U to be 0 at the curve X equal to T by 2. We can take it to be 1 also, right?
Which one? T by 2 means you are saying X equal to T. Yeah. But then you have to satisfy. But if you want to take X equal to T, then you have to see whether that line satisfies the RH condition. That is important.
No, I'm saying like at line X equal to T by 2, we have defined U to be equal to 0. We can define it to be 1 also.
That is not a problem.
And these two will be the only two weak solutions we can get because
weak solution is one. Sorry. Weak solution is a one. What is two weak solution? What do you mean by two weak solution?
Like
separately, they are the classical solution. Separately, U minus and U plus, right?
Yes, sir.
Separately, they are the classical solution. Separately, here U equal to 1 is a classical solution. U equal to 0. You can see U is a 1 is a constant function. It's a classical. Problem is this U equal to 1 is not a classical solution for the whole domain. You understand?
Yes, sir.
That is a problem.
So, sir, my question is like we defined U to, we can define U in two, like the only curve we are getting which satisfies the RH condition is this X equal to T by 2.
Yes.
And from there, I can define my UX to be like I know on the left hand side it is 1 and right hand side it is 0. On the curve I can define it anyway, right? Like on the first initial phase of the curve I can define it to be 1 and then I take it to be 0.
Yeah, that we can do. You can do. Yes.
And this will be the only weak solutions.
Exactly. Now I will just this example you will see the interesting thing. Yes.
Sir, if we define into two ways, then sir, uniqueness of solution will be violated, sir. Like
so first we have to show that yes. Very nice. I will come to that. There might be weak solutions are not unique. Okay. Clear? You will see. Weak solutions are not unique. Okay. Good. Very good.
Here we are only satisfying the RH condition, but we are not actually checking whether the solutions that we are getting are weak or not. I mean,
of course, that is why I said no. You have to check it's a weak solution. Check. Very good. You have to check this. Okay.
So do we have to do this exam as well? We have to.
You have to just check. You have to just see whether it's. You can check with the definition of weak solution. One is a bounded measurable function. You have to multiply with VT and you see whether it's coming then. You will see that it's coming. Okay?
Okay, sir.
Yes, you have to check. Very good. You have to check. This example will see you that there are infinitely way you can define a weak solution. And here problem lies. Then which solution you should take? Then we will not do. That is something a research topic. This is some called entropy solution. Okay? I will come to that. You take this example. Okay? So you know that if you write down the solution, if your solution u of xt is like hx. This is 0. This is 1. And characteristic curves are we have done this problem. Yes or no? So if along this curve u is 0 along this curve and it is 1 if along this curve. We have done this. U xt is 1 along. But how to define? There is no way how to define the solution in this part. Yes or no? We know that the ux equal to 1 when x less than 0 and ux equal to along of course along this curve. Yes or no? Yes or no? We have done this.
Yeah, yes, sir.
So now what to do with this place? How to define the solution here? There is no characteristic curves here. What we do? We have done, no? Any point you can have a characteristic which so the characteristic is here, point is here, so this is 1. In this way we have studied, right? So how to define the solutions in this place? Okay, one possibility. Always try to think pictorially, draw the picture. So, as he said, someone you define a curve like this. Okay, x equal to again t by 2. Okay, x equal to t by 2. Okay, and left hand side you define 1. This here like this. So here it is u equal to 1. Here u equal to 0. Clear? And this is your RH. It will satisfy the RH condition. This line x equal to t by 2. Same way. U1 xt is equal to 0 if x less than t by 2. 1 if x greater than t by 2. Clear? Is that clear? So you have less than c. This is 0, and here along this it is 1. Is that clear?
Yes.
Is the weak solution. You can check weak solution. Same way. And satisfy. Check. This you have to check. Of course, this is t by 2 count. That is, and it's a RH satisfied. RH condition satisfied. Satisfied. Okay. Another way. You define instead of this type of characteristic solution. In this place, the solution u2 look like, just write down, and also it will satisfy this. 0 if x is less than equal to 0, x by t if x is 0 less than x less than t, and 1 if x is greater than t. This is also a solution. Agreed? Huh? What happened? Yes or no?
So how did we define?
This is, you tell me how I define. If you check along this line x equal to t, the character it will satisfy the RH condition, everything. It's a smooth way I have defined it. Okay, if you just check. Okay. Okay.
Okay.
So,
Okay, sir.
so this is just, you just check how I define. U2 is this and U1 is this, and both are weak solutions. So the question is, both are weak solutions. Weak solutions. Both are weak solutions. Then there is no weak uniqueness. So we are in a problem. This is when we are talking about solution from a physical point of view. You should know the solution means there should be some proper way to define that this is a unique solution or something. We always want something unique, right? Then we don't know how to say that. So then something called entropy solution is defined. Entropy solution. We will not do this. Entropy solution. Okay. That means, or sometimes it is called physically relevant solution. Relevant solution. So out of these two, this one and this one, which are physically important, relevant, we have to check. Okay. Out of that, so we have to define and we have to impose some additional condition on the weak solution so that it becomes a weak solution, so that it becomes a unique solution. That means there is no, if I define here, there is no uniqueness. As I said here, where it is. So, anyway, I'm not so getting. So anyway, so there is no uniqueness as he mentioned. Okay. So the problem is then how to go forward. So we have to impose some extra condition, impose some additional condition on the solution, to get uniqueness. Okay, which is called entropy. You have heard about this entropy in physics. Of course, this is related to that, but we are not doing that. We will not do that. We will not do that. We will not do that. We stop here. Is that clear? Tell me, is that clear?
Sir, in that example, in the previous example, as we had that we had a region where we could not derive any information from the characteristic curves.
Exactly.
So we had the liberty to play around and
exactly.
So in all these cases, do we have the situation that we can have more than one solution or an infinite solution?
No, not always. In this problem we have it depending on the problem to problem. Okay.
Okay.
It depending on the problem to problem. Okay. Of course, it depends on the problem to problem. Okay, that is all for the first order PDE. I just briefly I will explain in integration by parts. Okay, because this we will use everywhere. At least you should understand the statement. Let omega be an open bounded subset of Rn with smooth boundary. What does it mean by a smooth boundary? I will tell you. Smooth. Of course, I will not tell you the definition. It is complicated. This is a smooth boundary. I am not taking this type of boundary, where this type of kink type, this cusp type places are there. We are not considering this. domain. Okay, is that clear? You understand? Where there is like this. This is called cusp. We are not considering those cusp. Is that clear? We are taking a smooth boundary. Of course, there is a definition of smooth boundary. I am not going in that, but at least pictorially this should be clear. Boundary del omega. If U and V are two continuously differentiable function, okay, integration by parts say omega del u by del xi v dx. This should be equal to minus omega. Shift the derivative to v u del v xi. You understand the derivative of partial derivative with respect to any I variable. Dxi is minus dx plus some boundary term. uv, the derivative will not be one derivative. uv nu I d sigma of x. Now I draw the picture. This is your cell S omega. This is your del omega. So at the point, any point x, this is the outward normal. Nu is the outward unit normal. If it's a smooth, then you can always define an outward smooth normal at every point on the boundary. Okay? At every point of the boundary, you can define an outward normal. Okay? So nu. So nu is an n-dimensional vector. So this is n1, n2 dot 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 ni dot 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 na. Nth n component is when we are derivating with respect to xi, the ith component of the nu will come. Okay? So del omega uv. Is that clear? This you should understand very clearly that this is the theorem, because I will be using this now and then everywhere in the after maybe 2-3 weeks after. When we will be doing Laplace heat equation and all those things. Is that clear?
Yes.
Clear? Okay. That's all. Now you can tally with your one dimension. What you do, A to B, F,
Sir,
by
what is sigma?
Sigma, what is sigma? Oh, okay. I will tell you. You know measure theory, right? This is the measure, Lebesgue measure on omega. Right? This is a Lebesgue measure. But when I am doing a measure in one dimensional less, you know the Lebesgue measure is 0, right? What is the Lebesgue measure? What is the n dimensional Lebesgue measure of? So let's say this one. Let's take a ball, R2. Take a ball. So you know what is the Lebesgue measure of the ball. So what is the Lebesgue measure? Two-dimensional Lebesgue measure of the circle. What is that? What is the two-dimensional Lebesgue measure of the circle? Circle means the boundary.
0.
What is that? Exactly. Two-dimensional measure is 0. That means I cannot work in that measure. Yes. So this is called surface measure. This is called surface measure. So this is actually one-dimensional less measure. So that we have to. This is the integration on the surface, not on the solid part. You have to integrate with respect to along this boundary. So boundary is one-dimensional less object. Like let's take R2. When you are taking B2, when you are taking ball, this is a two-dimensional object. What is S1? S1 is a one-dimensional object, because this is just a boundary. This is just a boundary. Okay. That means this is in the, if I do in two dimension, dx is the two-dimensional Lebesgue measure, but on the surface this Lebesgue measure is 0. So we have to define a new measure that is called the surface measure. Surface n minus one-dimensional measure. Clear? You should have done this in the measure theory course. When I teach measure theory, I do these things. Anyway, though this is the surface measure, and this is the. Is that clear now? So when you are doing the one-dimensional integration by parts, you just see A to B, F prime G. You use this formula, minus A to B, f g dx plus a, this is b. What is the unit? So there is no integration because this is the one dimension. So what is this? You take this to be plus 1, this to be minus 1. So f g into minus 1 plus f g into plus 1. But all this at the point, this point is at b point, this is the point, sorry, this is the a point, this is the b. So finally you got a to b f, sorry, g prime dx plus f of b into g of b, because of minus, this is minus f of a into g of a. So this is your integration by parts formula, nothing what we have done here. Understand? Yes or no? At least, of course, there are many plus where I think you haven't understand, because the problem is del omega, and so at least I make you something, right? You understand, right? Is that clear? So you understand, if I work with same dx, then it is this integration will be 0. So there is no meaning of that. So you have to define a meaning on the integration on the surface. That's why you have to define a one dimension less measure, which is called the surface measure. Clear?
Sir, if you could provide us with some reference on where to look upon this, so
don't
that
go for a reference. Don't go for a reference. Just assume this is in this formula. Is there is no problem? You agree?
yes, sir.
Okay. Just you do this. I will explain you as the time as we go forward. Okay? Because if you go there, they will complicated things. They will say something called Hausdorff measure and many things it will come. So it will be more complicated for you to understand. Okay?
Okay, sir.
Okay, so at least you should understand this formula. That's all. Don't have to read the proof or anything else. If I now want to say what is the surface measure, it will take 2 days. If I want to prove this theorem, it will take another 2 days. Before that, I have to define what is a del omega, what is the meaning of a smooth surface. There is a proper, actually this is a manifold. This is a parametric manifold. All those things I have to define. Del omega is actually a parametrized manifold in n-dimensional. So it's actually n-1 dimensional manifolds. So all these I have to tell you. Okay, it will take another 6-7 class to make everything clear here. So don't go for a reference or something. At least you should understand what I have said. That's all. Okay, this maybe you will learn in differential geometry course or something else, somewhere else. Okay, is that clear, Deepak?
Yes, sir.
Okay, good. Okay, anything else you want to ask me? So this is the end of the first part of your course, PDE1. That is the first order PDE. Next, we will do something called Cauchy-Kovalevsky theorem and all analytic functions and all those things. Let's see what we will do from Thursday, because Monday we will be missing a class. So let's see. Okay, clear? Okay, do well. Best of luck. Thank you. Anything else you want to ask me, or okay, it's fine?
Sir, could you please explain how we use the integration by parts in the motivation that we did?
That you should understand. Now you check. It will not be a problem. Okay, you check.
Okay, sir.
You check step by step. I have explained you. You just check with the problem. Okay. Okay. Thank you.
Thank you, sir.